Finally, all right. Good morning, everyone, and welcome. I was very much looking forward to today. We have a new chapter. It's the first time this chapter is part of the course. Interpretable machine learning. We've been touching upon that a couple of times in past sessions, or rather circling around it every now and then. We've been discussing the relevance of interpretability, and today I want to provide you an overview of the research, and in fact this is very current stuff because interpretability is a hot topic at the moment. So I want to give an overview of the current research on how we can dig into predictive models and understand what it is that they picked up from data. And because it's such a popular topic these days, the number of techniques that exist have grown tremendously. In the last year, or let's say the 2 last years, and one of the objectives for today, therefore, is to categorize the field a little bit. The 2 main chapters are what I call global explanation methods, and then in the other part we have local explanation method. And very briefly we'll touch upon example-based techniques, which are yet a different type of approach. In general, what you see from the agenda, when we talk about techniques to interpret machine learning models, one way to think about them, this interpretation or explanation method, is whether they are applied at a global or a local scope. And we shall see very soon what that means. But let's first of all remind ourselves about interpretability and its importance. I've compiled this slide to just note down some of the points which I think we have been touched on in past sessions, why we care about interpretability. We do know that, albeit the examples that I commonly use in the course and that we consider in the tutorials maybe not being mission critical, but we do know from the press and the media, blogs, etc., that ML is used in an increasing number of mission-critical applications, which stresses the need to know exactly what's going on in these models that are then used in mission-critical settings. We've been discussing a lot about predictive performance, how we can assess predictive performance, and a little bit on why some models may do better, why ensembles may do better than non-ensemble techniques. We've been discussing that. You have a very solid understanding how you can quantify the predictive performance of a model, but in many cases, prediction or predictive quality is just not enough, gives you only a partial picture, and you need to understand what's going on in a model to augment this partial picture drawn only by predictive performance. And well, I have a lot of slides, so let's speed up a little bit. The other things, we talked about compliance, legal requirements, we talked about robustness, and many of that will pop up again in today's sessions. But bottom line message here is interpretability matters, and the fact that so many scholars these days think about it and publish papers on the topic further enforces that, I believe. One such paper that you might want to read is the one of Lipton, an easy read, fairly comprehensive overview of the field. I'm borrowing his a quote from that paper here, where he's arguing that the demand for interpretability arises exactly when there is a mismatch between the formal objective of some supervised learning model which typically is low out of sample error or low generalization error, and, well, the real world costs in an application settings. And as economists, we know that, well, that is pretty much the case anytime we use a model, because the different types of errors we may make, or a model may make, in the vast majority of business applications will be associated with different costs. But more generally, this quote further points out this view that predictive performance that we've been focusing on, in practice, it's just not enough in the most number of cases, and then we need to understand the models on top of that. Let's take a very brief excursus into the field of compliance and regulation. I'm sure that you have heard about the GDPR regulation, the Generalized Data Protection Regulation, which was enacted in May, I think, 2019. It's an EU regulation concerning, various matters, in fact, related to personal data and measures that companies have to apply when they collect personal data and personal identifiable data. It's a very big topic in any company that processes data, i.e. any company these days. Sharing of data became, and still is, a very big topic. Organizing that in a compliant way, etc., etc. And amongst other things, this regulation, GDPR, governs algorithmic decision-making, which is maybe the most important aspect for us in the scope of this course. When it is allowed, when it is not allowed, what needs to be ensured by a company using algorithms to make decisions autonomously, what this company needs to ensure so that these decisions are compliant, or that the very idea of making decisions by algorithms about human beings, like decisions on loans or other types of decisions on insurance tariffs or whatever it is that you might have on your mind, when this is compliant. And what often comes up, if you read about GDPR and algorithmic decision making, you will typically hear about a right of an explanation, which then in a nutshell means that we as individuals, if we do business with a company and this company uses some algorithms to make decisions that affect us, we have the right for an explanation. That's in a nutshell what it is about. And you could say this is a very strong argument why interpretability matters, that if you as a company use algorithms to make decisions, then your customers or the people you do business with have this right. Preparing for this lecture, I was digging a little bit deeper, and as a matter of fact, when you hear about the right of an explanation, and you might note that this part of the EU regulation is actually not legally binding. So when EU member states translate that into national law, it's open whether this right of an explanation really comes into play or not. So it's questionable whether we as individuals actually do have a right of an explanation or not. That will depend on the national interpretation of the EU guideline, in fact. And this recital 71, where the idea of a right of an explanation is articulated, it's actually buried down in the depth of this framework as an addendum. So what is it that I'm trying to say here? We may actually have a right that any algorithmic decision that affects us is explained. So yes, I'm just trying to further motivate the relevance of interpretability. At the same time, I'd like to point out that right as in a right, how we would understand these terms, well, maybe we do not have this right after all, because the way GDPR deals with this right is rather vague. But anyway, coming back to Lipton's paper, another useful list from that paper would be this one, where he's arguing that what we actually mean by interpretability is also a bit vague. Interpretability is a term that's not so easy to define, or the interpretability of a machine learning model is not so easy to define what that means. And because of that, he, looking into previous literature, compiles this list of desiderata. So what an interpretation method should deliver. Instead of giving a crisp definition, model interpretability is X, Y, Z, he comes up with this list, and I believe this is a useful approach. Any technique that promises us to interpret some black box type of machine learning model, be it a neural network, a random forest, a boosting machine, whatever. What should it really deliver? And one of the things here is trust. Building trust in model recommendations, well, that's a no-brainer, really. In fact, it's somewhat covered by the predictive accuracy of a black box model, because if it predicts accurately, then we can have trust that the model does well, does its job. But we do know that our ways to assess predictive quality is typically limited to some sort of cross-validation setting or out-of-sample setting, as opposed to a real-world deployment of a model, and that we therefore have this effect of our data sample as opposed to the wider population where the model is operated or does operate in. So trust, in addition to accuracy, also refers to an interpretation method should build trust that once we deploy our model to production, it will do sort of as good as it did in our simulations. That's something we would like to see from an interpretation method. Just make sure we are on the same page. The idea of this list here is to map out some of the requirements against which we can then judge concrete approaches, interpretation methods that will come shortly. Lipton's second point is causality. The models that we use are correlational and not causal. We can build a highly accurate scorecard to process credit applications, and in this scorecard, an algorithm might have found a rule that whenever a credit applicant has a high bureau score, high FICO score, or in Germany, high Schufa score, this applicant actually is a good credit risk. Possibly an algorithm will have found such rule. That does not mean that we are maybe a good debtor, a good borrower, because we have a high bureau score. The two things go together, but the bureau score, the Schufa score, does not cause us being a good credit risk, right? And by achieving interpretability of the model, then hopefully we get some cues, understanding how a model works. We hopefully get some cues what causal drivers might govern the process, like the repaying behavior. If we have a model, it predicts well, and by interpreting this model, we learn that the amount of debt that we accumulate is correlated with risk. The more debt, the more risk. Sort of intuitive, right? So that is a cue that me having too much debt makes me at some point unable to repay all that debt. So here we have a cause-effect relationship. And if I can interpret my model and come up, or can observe such associations, high debt, high credit risk, that gives me some cue that there might be something like a causal relationship here, which I could then test using other techniques. Machine learning alone is not enough to establish causal relationships. Then we have transferability, which again refers to the difference between our training data population and the test population, and interpretability. It's related to trust, can build trust that we can deploy our model. And referring back to the previous quote, predictive performance is a partial picture. If, as a company, we want to improve processes, typically good predictions are not enough. If we have fully automated credit screening systems, that's nice, but in order to identify new appealing segments of customers, where we could launch marketing initiatives, customer acquisition campaigns, for example, if that is also our aim, we need to understand, well, how does a good customer look like? What are the drivers that cause customers to be good borrowers to then inform our marketing strategies? Or if we build a model to predict when some machinery in our manufacturing hall breaks, so that we can proactively check and maybe repair this machinery, then understanding what causes the machinery to break could also help us to, well, redesign our machinery park or the way we operate these machineries. Getting insight on top of the actual prediction typically is very relevant. And finally, fairness and compliance also comes in. There might be regulation, as in banking, where we need to demonstrate to regulators certain patterns of a model and need to understand these models for that reason. And also there's increasing awareness for algorithmic discrimination, that minority groups are affected, discriminated unduly by algorithms. And in order to diagnose and then afterwards do something about algorithmic discrimination, we also need to be able to dig into our models and understand how they use certain data pieces and in which way, how they might use a data piece such as gender or ethnicity or something like that. So many reasons why the topic matters. And as we see here, many requirements or features that we would like interpretation methods to show, to exhibit. And as you would guess, there is no free lunch to be won here. There is no single method that would score equally well on all these criteria. But as already said, there has been quite some progress, and today we can do quite a lot of things. And before looking into individual techniques, here are some more characteristics of different approaches to achieve algorithmic or model interpretability. First of all, there are many techniques which are interpretable intrinsically, like linear regression or trees. Linear models and trees, they are often called white box models. There are also machine learning models, so definitely there are techniques, many techniques that are intrinsically interpretable, where we have no problem whatsoever. And we can distinguish these from auxiliary techniques, post hoc explanation methods, which we apply to a fully grown black box model and then try to dig into that black box model and understand what it is doing. So these two branches can be distinguished. That's one thing. And I give you some examples of what these post hoc explanation methods, they will be the focus of today, what they could deliver you, like feature summary statistics or visuals, example-based explanations. And these outputs of an explanation method are yet a different factor along which we can categorize the research. whether a technique only works with a certain type of model, like a neural network, or any type of black box model. That's yet a different characteristics along which we can distinguish different methods. And what I briefly touched upon before, global versus local methods. Global means that you have a black box model and you are trying to extract rules from that model which tell you how the model translates feature values into predictions in general. That's a global approach, and examples come soon. And contrary to that, a local approach means that you have one case, like one credit applicant, for example, and you produce a prediction for this credit applicant, and your explanation method tells you then, now for this single case, she got rejected because her debt is that was detrimental because it's relatively high, her age is this, so that's rather young, that was also detrimental. Her academic degree actually is master, which is quite good, so there is a positive rate. For each of the features, you get a quantification how important that feature was in the prediction for the individual case. That's key. Local means individual case, and whether it contributed to one class or the other. That's a local technique. And again, examples come soon. And before going there, an entirely different topic that is often confused, unfortunately, is the topic of algorithmic transparency. Take, for example, a gradient boosting machine. You get these predictions. We talked about the boosting principle. Let's agree on the fact it's not straightforward, right? It's not so easy. Or if you prefer, think about a neural network, the internal mechanisms. It's not so easy to fully understand what's going on there, all the math, all the stats that's underneath. That's not so easy. That, however, is algorithmic transparency. Even if we are not able, I mean, you hopefully will be able, but the average population might not be able to understand in detail what's going on in a gradient boosting machine. We can still take the model and try to understand the input to output mapping of that machine, feature values to predictions. So algorithmic transparency is yet a different topic. It's highly subjective. What might be crystal clear to some of us might be very opaque because too messy for others of us. We don't talk about algorithmic transparency. Just know when people talk about the interpretability of models, sometimes they mean I don't understand the math that's underneath that model. That's their problem. And no technique can help with that or overcome the lack of good education. But the working of the model, mapping inputs to output, that we can interpret, and that should be the focus. All right. That was already said, just for you to read up. Models that are interpretable per se. This typically includes the class of linear models and tree, or maybe we should say shallow trees. And as a matter of fact, these techniques, linear models or shallow trees, are used in several of the post hoc explanation methods as a vehicle to extract rules from a black box model. So let's leave the introduction with that and now look at some concrete examples. What you can do to interpret your black box model. The first approach is fairly old, is not a nice word, but this approach has been around for a while, and in my opinion, it's underappreciated. There are different names. Some call it pedagogical rule extraction, others speak of surrogate models. There are some yet different terms. Well, let's look at the idea. You have a black box model, GBM model, and you want to understand how it works, how it maps features to predictions. What you could do is take some data you just apply your black box models to your data and produce some forecasts, as we always do when we assess predictive quality. So if we look into this picture, upper part is all very familiar, right? BB target is the black box model target, i.e. that's Y, and if we train a model on that data, then maybe for a whole lot set we can produce predictions. I denote these by BB forecast. So maybe for Emma here, our first customer, we were trying to predict some quantity, 150 euros, maybe her purchase value when visiting our shop, and she actually bought items worth 150 euros, while our GBM model predicted for Emma to buy items worth 176 euros, possibly. This is how to read the table. And what we can do next is just use this forecast as a label in a post hoc explanation task. So we create a new data set that consists of the same features. We have the same customers, we have the same features, age, income, gender. So these parts are just, make sure you read this graph right, they are exactly the same, right? And as fake target, we use the prediction of our black box model. The prediction of the black box model becomes the target variable of our white box model. And then we fit a white box model to this data, and here use any you like, use linear regression, use a shallow tree, whatever you like better, it doesn't matter. Some white box model. But the important thing is you fit it to this data set. And then, well, I give an example of what the outcome might be. The outcome of a WB white box could be something like a linear regression with fitted coefficients, 338.2 minus 8.3 times age, so beta age is 8.3, beta income is 0.09, etc. The thing is, this white box model, what it does is, it learns, it approximates what the black box model is doing, if you think about it. We don't model Y anymore, the actual outcome, we just model, using our regression, the prediction of the black box. That means we learn the functional relationship between the black box model and its forecast, between the features and the black box model forecast. We approximate this relationship. And that is a way to dig into the black box and see what's going on there. This tells you something about how our black box, maybe GBM, uses the variable age and how its use of age relates to income and how that relates to gender. We have the coefficients. We know approximately what's going on in the black box. Well, there is a trade-off, and that's the cost or the downside of this approach. Oh, not only this one. There definitely is a trade-off. And this trade-off is the white box model that you use can only approximate the black box. In my previous example, when you predict purchase value, you can check, let me go back, you could check. So what would be the white box forecast? Maybe here the white box forecast might be something like 175, and here it might be something like 95. So there will be some mismatch between the prediction of our white box model and what actually the black box model predicted. There will be a residual, and then we can compute something like an R-squared statistic to see how much of the variability in the black box forecast does our white box model capture to judge its adequacy. And if that were not a regression type of model but a classification model, what's commonly done is to construct a confusion table like that one, where we could tabulate the black box classification against the white box classifications, and then just produce an ordinary confusion table. And if you then compare the number of cases where the white box model predicted exactly the same class as the black box model over all the cases in your matrix, the resulting metric is called fidelity. Fidelity measures in general tell you something about the quality of the approximation, how good your explainable model approximates the non-interpretable model, the black box model. And there is this trade-off. The approximation, if it's too good, well, it can't be. If it were too good, then why would you use a black box in the first place? If you can replace the black box with a linear regression model with a white box model, there is no need to use a complex model in the first place. So the approximation cannot be too good. Or if you have some control over the approximation, let's say you don't use regression, but you use a tree, the question is how deep do you grow this tree? And if you grow it too deep, then the tree loses its interpretability. A tree with 10 levels comprises a complex set of rules. We might not be able to interpret that easily anymore as human beings. There is this trade-off here between the quality of your approximation and the interpretability of the interpretable or white box model. But you need to live with that. That's one way to extract rules, let's say, from black box models. And this is a global approach because, the focus is to understand how the black box uses features in general across all cases that it predicts. All the techniques that are in this part of the chapter are global techniques. You can find some slides on two-stage models in the handout. I'll skip over them. The reason I included the two-stage models in the first bit was that I like them so much. I wanted to interest you about it, but it's not necessarily related to explanation method. Let me skip these in the interest of time and come to a different type of technique that is very important, a de facto standard. That's something that you will definitely see and also use in industry or any time you work with these techniques. Permutation-based feature importance. A way to interpret a model, is to understand roughly on which features the model based its predictions. You can criticize that view, rightfully so, but one of the typical complaints or issues people had with machine learning models was that you don't really understand which features the model uses and which features are important or unimportant. You know nothing about the way it uses features. And these feature importance scores were developed to address this issue. Let's look at the output first. You see on this slide a standard supervised machine learning dataset with a target. In my case here, this is a binary target, credit risk, good or bad, and some features. And this post hoc explanation technique will deliver you something like the bar plot you see on the right-hand side, a quantification of the importance per features that you can then compare across features. So here you could easily see that our black box model bases its prediction very much on the variable age. And the second most important variable or feature in that data set, according to our black box model, was the feature number of accounts. And the feature income apparently was the least important variable in our data set. That is the type of insight that you get from permutation-based importance scores, and they are very popular. You can really just discuss it. It's a good exercise how valuable that is. Thinking about Lipton's desiderata of explanation method. Does a visual like that, an analysis like that, where you rank all the features according to your importance, does that build trust? Would you as a user have more trust using this credit risk model than only seeing its predictive performance? Or how about the other things? How about causality? Does it give us some cues what causal relationship might drive the feature response or determine the feature response relationship? Your example is one of the things that make people hesitant in industry. I have my prior belief. I have this model that's claimed to do better than predict sales, risk, whatever, better than I. One thing I would want to know is whether it agrees with my beliefs. And to some extent, such an analysis provides me this confirmation or disconfirmation, depending whether the outcome actually is in accordance with my beliefs or not. So yeah, maybe there is something that could help with building trust. You could take an opposite opinion and say, well, okay, age is important, but in which way? Is it if I want to be scored as a good credit risk, should I be young or old? Not that I can change anything about it, but you don't learn something about the way in which the feature drives the target. The sign of a regression coefficient, so to say, is missing here. So that's the disadvantage of the technique. It's a bit vague. It's debatable after all. Important for us, that's something we can use. There are ready-made tools for this type of approach. It's also global, of course. It is model agnostic. It works with any type of black box model, as most approaches we have today. I'm just coming from the previous lecture, and we had a guest speaker from industry, and there was this old discussion like some type of models like neural networks are less interpretable than others. That's all bogus. We have a rich set of explanation methods. Any type of black box, it really doesn't matter. GBM, deep neural networks, whatever exotic type of model you might have, provided it's a supervised model, you can interpret it using these techniques, or you can interpret it to some degree. The approach here with this permutation, I want you to internalize a little bit more because it's so prevalent. How does it work? Breiman was the one who initially came up with it, and then much later Fisher and colleagues, well, not reinvented it, but sort of wrote it up in a nicer way. The idea is the following. A feature, remember, we're trying to quantify the importance of the feature. So the very premise of the approach, a feature is important if my model suffers when the feature is not available. That's intuitive, right? If income is an important predictor of credit risk, and I deny my model access to a feature income, my model will not do so well. That makes sense. Now, taking out a feature is computationally problematic, causes computational effort. It's not so nice. Better way to do this is, according to Breiman, or then here Fisher way, you apply your black box model to some data and collect its prediction and collect predictive performance. So we have our trained model, in this pseudocode, we have our data, x and y, and some measure of predictive quality or forecast error, L, which is a function of the actual target y and the model forecast I denote by small f. So we find this measure, this, say, model error on the data x, and we store that. And then for every feature, we process features one by one. We just permute the feature. Permute. So we randomly shuffle the value in our single column, in our feature column, across all the instances that we have. This random shuffling, or you could also add noise. There are implementations where you just add noise to this feature. You sort of damage the feature. Shuffling is a way to do that. If you damage the feature, for example, through just shuffling the values randomly, the relationship between this feature and the target y will break. And if you then reapply your model to the adulterated data set, so the data set where you have one feature corrupted, and again calculate the error of that model, you get a second estimate for this error. So you have, in my pseudocode here, you have E-ORIC, the original model, and you have E-PERM, the error after permuting one feature. And then comparing these two values by means of a ratio, here you can establish feature importance as a ratio of the two error figures, or also the difference. That doesn't really matter much, and every version is around in some package or the other, but it's always the same concept. If after corrupting the single feature, the error increases a lot, that's the key thing. If the error increases a lot when I corrupt one feature, that feature was important. And if the error vaguely stays the same, that feature was unimportant. And then maybe with some normalization and other magic, you can create these bar plots of feature importance. Permutation has some statistical approaches that are maybe desirable, but you could imagine the very same approach with just deleting all the values of these features and plugging in some random values. It's the same concept, and then you would not expect that this improves the model in some way. Well, functionally, you could, well, let's look at these statistics here. We have, let's take this one. We take the error of the permuted feature over the error of the original feature. So if the error of the after permutation were lower, so the model improved, right? So this quantity were below 1. Functionally, you could observe values below 1, but this then is a sort of noise which implies if the feature was meaningless beforehand, if the feature was close to random beforehand, then permuting it doesn't change anything. So the magnitude of this E-PERM over E-ORIC that I observe, it will always be around 1, but could be a little less than that. So if the feature was unimportant beforehand, there is no guarantee that my model will get worse if I permute it, right? That's maybe important to note, but with good features, permutation is guaranteed to hurt. And this is what you want to know. You also find Bryman's original idea in the handout. In a random forest algorithm, the random forest algorithm has some nice properties that allow you to implement this concept very easily and efficiently. That has to do with out-of-bag examples, etc. It's not important. Let's not go there. I want you to understand the concept, and then in terms of pros and cons, advantages that we could agree upon are that it's fairly easy to understand. I take my error, I corrupt a feature, I recompute my error, and compare the two error estimates. For a good feature, corruption must have hurt the model. That is fairly intuitive to understand. That's something you can communicate to anybody. That's a pro, for sure. It avoids any sort of costly re-estimation of the model. It's relatively efficient, especially when you compare this approach to something like stage-wise regression, where you iteratively re-estimate models with different feature subsets. That's way more costly. So another pro. Well, account for feature interaction. That needs a bit more thinking. If you have two features that work together, like debt and income, they relate to one another. A feature interacts with another feature. So, well, roughly put, the beauty of one feature emerges only if you have the other feature in your model. So you have this pair, this couple of features, and you break one of them. This will break the interaction. So let's say you have a feature that does not work at all alone, but very well when together with another feature. So there is no main effect of that feature, but an interaction. It's rather theoretical, to be honest, but let's assume. In permutation importance, corrupting the single feature, the single element in this couple, will break the interaction, and therefore you account for interactions. That is a pro. You could also say, that's also a con, a disadvantage, because the net value, the net importance that you observe for a feature is the combined effect of its main effect, how well it works individually, plus all possible interactions with other features. So whether you see it as a pro or a con is maybe a bit debatable. Disadvantages, well, yeah, you need actual labels, access to them. Otherwise, it doesn't work because it's based on error values or performance values. You have a random element by the permutation, and the random variation could be substantial. So you do this, you randomly permute a feature income, establish feature importance, and then you repeat everything. You again randomly permute the variable income, the feature income, establish feature importance. The results can change substantially because of this random element. There is no easy way around it. If you feel this is a problem, then you could basically repeat the computation of these importance scores multiple times and then hope to average out the randomness. That's normally not done, but the better packages, let's say, will already give you in their results an indication of how large the random variation is. And well, I'll dig deeper into that issue, but let's note it here as well. The approach is vulnerable toward correlation. Correlation is a problem. If features are correlated, your view on feature importance will be biased. So you need to take account of feature correlation. Or you need to check whether features are correlated, and if they are, be very careful interpreting these feature importance scores. We'll come back to that in the scope of partial dependence plots. And one final remark in terms of tooling. Permutation-based importance is a standard approach, and there are many packages that you can use. Some packages, when used together with random forest, might by default produce a different or use a different approach to compute feature importance. In Bryman's random forest paper, there is an alternative approach to achieve the same result, these bar plots of feature importance. And the alternative approach was based on the Gini coefficient that's used to split the individual trees in the forest. Later, it was shown that this approach is flawed. You must be alert of that. Whenever you look at the feature importance of a random forest, or nicer setting, you sit in a presentation and somebody reports on feature importance for a random forest classifier and you want to ask a smart question. Is it really this permutation-based importance that's based on the error of the model, or is it the other version, because the other version is flawed? But unfortunately, some packages still produce that by default. So here we need to be a bit careful. Rule extractions with a surrogate model, number 1. Permutation-based importance, number 2. Both popular, easy to do, and thus useful. The next approach in that family, PDPs. They yet take a different approach towards interpretability. Here, with PDPs, you could say we go beyond permutation-based importance. Let's say previously we established, income is important when we predict credit risk. We learned that from the permutation-based importance, okay. And I was saying, well, you know, with permutation-based importance, you may know that income, a feature, is important, but you don't know whether higher values of the features are associated with higher values of the target or vice versa. So you don't know the direction of the feature-response relationship. There come PDP for rescue. It's a partial dependence plot. Statistically speaking, we marginalize over all the features but one or a small set of maybe 2 features and study how the model output changes with changes in the feature. That needs a little time to digest. Let's say we have debt. Let's say we have a feature in a credit risk model which is debt. And let's say our credit risk model predicts, well, what it usually predicts, PD, probability to default. So let's say it predicts P of that given X. Here I need to be a bit more accurate notation-wise. It's not X. I should put X as to indicate that the probability estimate of my black box model depends on my single feature that I'm focusing on. And then a PDP might look like this. That, in fact, would be the result for a linear regression model or a logistic model. Let's pause a little and reason what that means. That says that, okay, the larger the debt, the higher my estimate of the customer to default, the higher my PD. So higher values of debt are associated with higher values of default. And then we could say, oh, that makes sense. That's more plausible than the other way around. So that is good news. That could build some trust. And if this were the result, we could go on and say, and actually, you know what? This relationship is linear. Or maybe the PDP looks more like this. So the relationship is maybe not linear, but at least it's monotonic. The more debt, the higher the risk. This relationship still holds, just that the relationship is not linear, but a bit more complicated. And this works for classification, but the same idea. Let's say you have sales and you have price. One of the most beloved examples in marketing and business maybe. We could say, okay, well, low prices, high sales, high prices, low sales, and we could construct the PDP in the same way. Or we might find something like this, which would tell us some interesting effects. There is some point, if we increase prices further than that, sales begin to increase again. And arguably it's true. Some goods we buy because they are expensive and we know that others can't afford them, so we feel better. There are these type of goods. You just need to look at the cars that drive past the street and you see what this is, right? What effect that is. So the partial dependence is conditioned on the effect of all the other features. That's the good thing. You really marginalize over the other features and see, keeping everything else constant, how does my model prediction? It's only the prediction change with changes in this single feature, and that tells you something about the the nature of the relationship between a feature and what your model does with that feature. And that can be very useful to confirm your expectation, your prior expectations, or, well, show that a model does not agree with your expectations. That's the PDP. Formally, you could state it like this: the partial dependent function empirically is an average that we construct by averaging over all the features. The formula is nice, but let's look at a concrete example. Let's take some data, and let's say we are interested, well, I'm just trying to explain the formula. Let's say we are interested in the feature credit amount. And in my example, please note that credit amount has only two distinct values, 25K and 50K. I note these two distinct values, and then I create, well, hypothetically, I create a data set where I copy and paste all my data points. If I have n data points, 5 in my example, after this copy pasting exercise, I have 2 n data points, so 10, where in the first half, all data points get the value credit amount equal to 25K, and in the second half, they all get the value credit amount equal to 50K. And by copy pasting, I duplicate all the values for the other features. So this is how my data set looks like, and then I can average, well, I effectively average over all the other features. And study now, okay, what would happen if my customer has credit amount equal to 25,000 over all the other features I average. So this is what I end up with. That's my data structure. I also average the model predictions, which might be something like 45% and 75%, maybe. That might be my model predictions, averaged in this way. And then I can readily plug these into a plot, and there is my PDP. Well, we can also then formalize this a little bit more, which was the formula, but I think the example is easier to understand. And this example was for numerical features. For categorical features, it's even easier than that, or it's, well, the same way maybe. You just you duplicate all your data points for each level of the features, then do the averaging, and then, well, PDP sort of looks like that for a categorical feature, because you have distinct levels and no values in between. And this is how they are produced. Here are several packages that you can use in order to produce these charts. So many packages. EML is maybe the best one. PDP was some of the first ones that's useful. EML is one of the best packages because EML, Interpretable Machine Learning, it has pretty much all of the stuff we've been discussing here available in it, so that's a very useful package. And the key deliverable here is that on top of feature importance, we can diagnose individual features and understand how exactly they relate to a target. If the correlation is positive or negative, and also whether it's linear or monotone, or whether there is a nonlinear pattern, which could be very interesting as well, as in the price example, right? Some packages allow you to create three-dimensional PDPs, and then the question is whether you can really interpret these surface plots or these three-dimensional plots easily or not. Well, whenever I use that in papers or also in industry, I never went to two-dimensional PDPs because I think they are too hard to grasp, and always stick to the one-dimensional version. One remark, in this example PDP plot here, you have these little rugs, they're called rugs here, you know, these little bars. The idea of these bars is to indicate the mass of actual values, where the data is. So this little guy here, you could read it as, in the actual data, one of the observations had a value for salary of 20K. This is how to read these things. And you typically do notice that there are sparse areas, like here. In these sparse areas, there is very little data available. Very few observations have feature values where salary is something like 60,000. And in such areas, you have to be careful when you interpret PDPs, because the graph shows these averages, but in areas where there's very little data, the average is not very robust. So if, in this example, the PDP suggests that the higher the salary, the higher the probability of the client being good. That would be the way to read this PDP. It's a bit bumpy because this is a small data set. That's why it's bumpy and not so smooth. But overall, we do see some linear, maybe slightly decreasing tendency here. So more salary is good, if, well, or associated with higher probabilities of customers being good risks. And then there is this odd behavior here where the probability of good drops sharply. That is an artifact. It originates because there is little data available to estimate the dependency between large incomes and model outputs. And you have to be careful in interpreting these areas. And this is why these little rugs are so useful to depict where is the mass of the data. And some packages don't provide that. Typically, well, sparse areas occur on the extreme sides of a feature, very small or very large values. Typically, but not necessarily. So, well, long story short, you want to select a package, or when you produce PDP plots, you want to produce plots where you include these rugs to indicate where the mass of the feature value lives. Many advantages, they are also fairly intuitive, useful, etc. One big issue, the same as before, correlation. Correlation between features will hurt you. And essentially it's the same reason why correlation is detrimental in the permutation-based importance. And here I'm detailing this a little bit. What's the problem with correlation? A similarity between how PDPs work and how feature permutation works is that you create artificial data points. In permutation importance, you permute feature values, and by permuting feature values, or plugging in random values for that matter, you create data points that do not exist, or that have not been observed. And in PDPs you do the same, because you duplicate your data, but in the first half you have only always the same value for the feature of interest, like 25K in my previous example, and later on we had 50K, but also we had artificial data points, right? I'm always a bit unsure whether you know what I'm talking about. This was the PDP example, right? Where we duplicate records, manipulate them, and by doing so create artificial data points. Very much as in the permutation-based importance. The issue with correlated features is, in such approaches, you might create data points artificially that are extremely unlikely or even impossible. But then you average over these impossible data points and produce outcomes, like estimates of feature importance, on the basis of very unlikely data, which is an issue. So for example, if you have a model that tries to predict the value of some apartment, and you have features like number of rooms and size of the apartment, I mean, clearly there is a correlation. But now, if you naively produce a PDP, maybe you have an apartment there that was 30 square meters in your data. Why not? Why should you not have an apartment in your data that had 30 square meters? Well, when in Berlin, I live in one of these. So clearly that's a possible value. And also in your data, you have this beautiful, nice, big, posh apartment with 6, 7 rooms, or maybe some of the old style of building, 7, 8 rooms in one apartment. Also, this is a possible feature value for number of rooms. But through creating this artificial data, you might create a data point with, I don't know, an apartment that has 30 square meters, but 7 rooms. And that's not going to happen. So that data point, because of the correlation of room size, of number of rooms and apartment size, creating these artificial data points leads to very unlikely points, but they are considered in subsequent calculations. And this is why PDPs as well as random forests are vulnerable toward feature correlation, and why you as an analyst need to check whether there are correlated features. All right, there is an approach, more advanced approach, to the ALE plots from Epley and Zhu, which overcome that. Instead of the partial dependence, they look at conditional dependence across features. This overcomes correlation. It's slightly more complicated to understand the underlying reasoning. This is why I was focusing on PDPs that are also more popular. But note that if correlation worries you, there are alternatives in even more recent approaches. Another issue is that you might overlook heterogeneous effects, i.e. interactions in PDPs because of the average. Yeah, the example is intuitive, right? If you have a feature which interacts with gender, and the relationship to the target is positive for all females and negative for all males, averaging, the relationship to the target would then be 0, and the PDP would tell you, this feature is not important, whereas in fact it was just interacting with gender, but you didn't notice that. There are techniques available to overcome that problem, these heterogeneous effects, and they are known under the label ICE, individual conditional expectation curves. They are created in the same way as PDPs, just not at a gross level. You don't average over all the data points, but you depict all the data points individually. And then these plots look like these. Here you also see these rugs I was commenting on earlier on, where all the data lives. And that could be like a PDP, but created for each single data point in your data set. I borrowed that from, by the way, this website from Christopher Malner. It's a beautiful website. He has a free ebook on interpretability research, and it's also available in the references. I'm using this a lot for this chapter. It's a very great, very good website. If you want to know more on certain techniques, I recommend this website as your starting point. Well, and we don't really see that in this example, but a heterogeneous effect in an ICE plot. Overall, the tendency that we see here in this plot would be that so it's age, and the target is it's a bit morbid, predicted probability of cancer. And overall, the story told by this plot would be that for most data instances, risk is low for younger ones, and then there is a certain age where this increases, like 40, 45 maybe, so very bad news for me, where the probability goes up and then stabilizes again. That's the overall pattern. And if we had a large number of data instances, data points, people. And remember, one data point, one line that go like these here. I mean, we can also use these. Here, these people, they're relatively young, but still exhibit a high probability that deviates from the overall trend. If we believe that the number of lines that we see in that area is large enough, enough people are affected by that pattern, then maybe this is because age is correlated or is interacting with another variable that we don't see here, and that would be the way to spot a heterogeneous effect in an ICE plot. In a simplified, let's simplify that a little bit. If this is our space, and we have a couple of data points that exhibit this pattern, but we also have a couple of data points that show another pattern, then this might be the reason why there is lack of consistency in the dependency between the feature and the output. That may be because the effect of this feature actually is heterogeneous and differs across different groups, gender groups or educational groups or whatever. And I want to leave the part on global interpretation methods with that. Let's try to summarize this a little bit. You have seen permutation-based importance, crucially important, and PDPs, which is the thing that you then need on top. And with the two together, you already have a lot of information to report about your black box model. Which were the important features? And then for the important features as identified by permutation-based importance, you can create PDPs and tell more about how these important features govern predictions and whether these make sense from a domain perspective. So they are a useful tandem. They work nicely together, the permutation-based importance and the PDP. We also talked about surrogate models, which I would judge an orthogonal approach, where you have a white box model that overall tries to approximate your black box model and then create something like a rule set. For example, if you use a decision tree, a simple decision tree, as white box or a surrogate model. And you have also seen that all these techniques are not perfect, have issues, and more advanced versions exist. So you have a starting point if you need more or want to learn more as far as the global techniques are concerned. That should equip you quite well, I hope, for the applications that await you in your studies or in industry. And we could now turn our attention to local explanation methods. We can't obviously cover them in as much depth. One approach, LIME, I want to elaborate in a bit more detail. It's one of the go-to techniques these days. CHAP values are, if you wish, the challenger, newer, better than LIME, but much more costly. And, well, these counterfactuals and adversarial examples, I will just briefly mention them. Very interesting stuff as well. I just want to give you a vague idea what these is and why these might be interesting. But first things first, LIME. Local, interpretable, model agnostic explanations, or LIME. The name is good. Why is it chosen? Because it highlights the characteristics. It's a local technique, it uses interpretable techniques, and it works in a model agnostic manner, so with any type of black box model. Remember, local means that we try to explain individual level prediction. Goal is to understand why a black box model made a certain prediction for one case, one data point, one client. And you can look at it as an overall framework, and then the paper by Ribeiro, or however they are pronounced, famous paper, that won the team by now, I think, 2,500 citations, which is quite a lot for a single paper. They had a concrete implementation of the framework. And this graph is from their paper. The thing I find interesting here is the output of Lime, and I reproduce that in a credit scoring context. Before going there, the overall setting would be, you have a model, it makes predictions, and then for individual subjects, clients, credit applicants, whatever, eventually you want to have a human decision maker checking these predictions so that the action that is taken actually is correct. And you may be able to see that from this picture. The context that Ribeiro and colleagues had in mind was medical diagnosis, where you have a model that is fed with some symptoms like sneeze, weight, headache, no fatigue, I'm not tired but have a bad headache, my weight is X, I'm that years old. Then makes a certain prediction, like, oh, this guy is suffering from flu. And then Lime comes in and explains, for example, to an MD, a medical doctor, why the model thinks that this person has a flu. So that the doctor can verify, does that make sense, is it actually true? And the settings, the utility of that, we can again discuss. Whether it actually is the human that makes the decision and just uses the model as a way to be quicker in making decisions, or whether it's a way to build trust, or whether it's a way to just check that automated models act in a sensible way. Various use cases where Lime could be beneficial, and as promised, this is what you get. That's the output of Lime. Let's try to understand that. First of all, note this part. That's also part of the output. We have a single credit applicant, a single case in general. And you know, my pet example is credit scoring. So we have a single credit applicant. We know for this applicant what feature values he or she had. We know the actual class. Let's say our applicant in fact was a good risk, and let's say our estimate of her being good risk was 75%. That is the prediction. And now we want to interpret this prediction for this credit applicant. That's what Lime is trying to achieve. So what you get for each of the features, and let's assume we have 4 features: age, salary, credit amount, and whether there was any sort of collateral to secure the loan. For each feature, we get a score. We can compare the relative magnitude of these scores. And this score is also either positive or negative, meaning that, so the way to read this is that, ignore the values on the axis. The way to read this is that age has contributed to the forecast of 75% of her being a good risk. And so has the fact that she apparently has some collateral to secure her credit, whereby the fact that she had collateral to secure her model was roughly twice as important as her age. And salary also, the way it was, created the model to increase the probability of her being a good risk. So because of her salary, she was scored higher, you could argue. And the credit amount she applied for, well, that actually decreased her prediction by a quantity that was even a little more substantial than the effect of salary. That would be the way to read this plot. So estimates of feature effects we get, and more accurately, we get estimates of effects for a set of features. Our scorecard could use more features, while Lime would only produce us these 4. And this is to help us understand what causes the prediction. So sometimes people say Lime is a causal approach, which is true. The causality it establishes is how feature values cause the prediction. The prediction, of course, can be correct or wrong. That's a different story. The causality we established is from feature values to predictions. And that's the focal attention point of Lime. Right, I realized we had some delay. I don't want to rush with too much. You got an idea what Lime is about. I'll briefly come back to that in the next week because I think it's an important technique. So I don't want to skip that. A pity we lost some time with the technicalities in the beginning. So we'll take that into the next week, where, by the way, we'll also talk a bit about imbalance and cost-sensitive learning, so a new topic. But I realize time is up, so let's stop here. Thank you very much for your attention, and I, wish you loads of fun in the tutorials. Thank you very much.